Yeah, so I'll be talking today about existential physics. Last year, I gave a talk about this at a literature festival somewhere in the UK. And when I opened the booklet, I saw that I'd be speaking about the meaning of life. So I was a little bit surprised, and I promise it's not going to be quite as existential. So if I would be listening to this talk as a student, I believe I'd find it a little bit esoteric, or maybe even vague. It's a topic that, okay, no, this is not working. It's frozen. Okay, I'll just continue talking while she's trying to figure it out. It's a topic which lives at the intersection of the foundations of physics and philosophy, and even a little bit of religion. And I'm afraid that this intersection doesn't have a very clearly defined boundary, which you should see in this image, if you could see the image. Right, there we go. So the boundary is kind of blurry. And that's what we'll be talking about today. This blurry intersection of science, philosophy, and physics. So when I was a student, I was really proud of having learned how to do serious hard calculations with lots of mathematics and data and so on. So how did I end up in a position in which I'm talking about something as esoteric as this? Well, what happened was that I wrote a book about what's going wrong in the foundations of physics. This was my first book, which was published a couple of years ago. And it was very critical of how we're not making any progress on the foundations of physics. We're still trying to figure out what dark matter is. That's a question which has been around since the 1930s. We still haven't figured out how to quantize gravity. We still don't know if the Big Bang really happened. We still don't understand the measurement process in quantum mechanics and so on. And I was trying to explain why that happened and all the things that went wrong in the foundations of physics. And after I published the book, I found it a little bit depressing, honestly, because it made me look like the kind of person who always complains about everything, stuff that isn't going right. And also, I was depressed about this lack of progress. So I thought I would like to remind myself of why I went into physics in the first place. And this is why I wrote my second book, which I'm talking about now, in which I revisit all those big questions that got me interested in physics in the first place. So, you know, if you end up finding this topic a little bit esoteric and vague, maybe just store it away for later. Maybe at some point in your career, you'll find yourself in a similar place where it helps to remind yourself of the big questions, the reason for why you started being interested in physics in the first place. So one of the issues that I quite frequently face, one thing which you might have noticed from this selection of translations of the book, my first book didn't have a publisher in the UK. It was translated into a lot of languages, but the British people didn't want to publish it. I'm secretly convinced it's because there's, if you just click that. Yeah. It was actually working. Oh, okay. Okay, whatever. So I'm secretly convinced it's because there's an S missing in maths. The French, for some reason, use the British title. You know, if you think that quantizing gravity is a hard problem, understanding how publishers work is a much bigger problem. Okay, so one of the problems that I encounter when I'm talking to people about physics is that they tend to say, oh, physics, I never liked that in school. And I totally get it, because just among you and I never liked physics at school either. because it was also kind of boring. You know, it was about how pendular swing ideal gases, something with atoms, useful, no doubt, but not particularly inspiring. It was only later when I realized what physics really is that it gives us a very rigorous way of reasoning about how the universe works in its entirety. And that requires a very careful definition of terms and logical deduction from assumption. And it has a lot of mathematics in it for this reason. And this mathematics has allowed us to infer lots of remarkable properties about nature. I think that this power of mathematics is generally somewhat underestimated, even by physicists themselves. So the idea that I was trying to capture with my second book is that physics is, yes, it is about the behavior of matter in space and time. But we get to know it as a discipline that applies only to inanimate matter, how lights work, atoms decay, rocks fall. We don't think of physics as something that applies to ourselves. But I think that physics is just so much more than this. It tells us something about our own connection to the universe, because we ourselves are also governed by those fundamental laws of nature. And this is why I wanted to call the book More Than This, which some of you, if you're old enough, might remember is also the title of the song by Roxy Music, which I've always thought it's really a song about determinism. And it's a somewhat depressing song if you look at the lyrics, why the sea on the tide has no way of turning, and so on. And yes, you know, if you look at physics, if you get a first glance at physics, it seems to be a little bit depressing, actually. We're all made of particles, and these particles obey the laws of nature, and everything was already determined at the Big Bang. And more than this, there's nothing. But I also think that this is kind of missing the point. So yes, we're all made of particles. All right. But the fascinating thing is that we're a big collection of particles that can do quite amazing things. Some people fly to the moon, others win Nobel Prizes, and God knows what you'll go on to do. So I think we have to see the full picture. So yes, on the fundamental level, we're all made of particles, but there's so much more to it. My publisher didn't like the title More Than This. They wanted to have the word physics in the title, and so they came up with this notion of existential physics, and I thought, that sounds pretty cool. When I grow up, I want to be a professor of existential physics. But it hasn't quite worked out yet. Yeah, so, but of course, this brings up the question, like, what do I mean by existential physics? So I had to make something up. And what I came up with is that it's physics which is concerned with those aspects that concern human existence. And that's quite a bag of questions, so to say. There's the nature of time, what changes, how does it change, why does it change, other things that can't change. The beginning of the universe, where do we come from? And also the question, where do we go to? How will the universe end? Can we say something about that? The structure of matter, what are we made of? Constraints, what can we do? Are there limits to what we can do? What do the laws of nature dictate? And limits to our knowledge. What can we know? Do the laws of nature actually set limits to how much we can find out about the laws of nature? So there are lots of interesting questions that I put under this header of existential physics. So this was the one reason I wrote this book, because I wanted to remind myself of all those big questions. The other reason is that as a science communicator, I spend a lot of time debunking headlines. You know, if someone goes and says, well, physicists have created negative mass, or faster than light travel is possible, or, you know, they've found evidence of parallel universes, or what have you. Then I'm the person who has to say, no, they didn't, no, they can't, no, they haven't. And I think that this is necessary, but it's also a little bit of, a killjoy, so to speak. And it sheds a light on me that I don't particularly like. I don't just always want to be the person who says, no, you can't do this. Every once in a while, I want to say, yeah, I think you can do this. At least there isn't anything that speaks against it. Okay, yeah, so when I wrote this book, I noticed that I was using those 5 words a lot. For all we currently know this, and for all we currently know that. And in the end, I just decided I'd take them out of the book and put them in the preface and say, everything I'm going to say is for all we currently know, because science is never entirely settled. And maybe in 5 years or so, we'll learn something new and we'll have to rethink everything I wrote in my book and everything I'm going to tell you. Okay, so let me start with the question that is the topic of the most popular YouTube video I've ever made. Was a complete surprise. It's now been viewed by 5 million people. I have no idea why, because it's a super technical topic. I think most people don't understand what I said in the video. I'm not sure I understood it, but people are definitely interested in it. Does the past still exist? And at first, it sounds like, the kind of question you can't possibly answer. But it's here where the power of mathematics really strikes home. So Einstein's relativity is basically built on 3 assumptions, but the speed of light is finite. The speed of light is the same for all observers and in all directions and so on. And nothing goes faster than light, strictly speaking, faster than light in vacuum, because the speed of light in medium can depend on the observer. Now, this brings up an interesting question. If you ask yourself whether you know that I am here right now. The issue is you can't really tell because you don't know what now means. You see, every time you look at me, it takes a little time for the light from me to travel to you because the speed of light is finite. So you always see me as I am a little bit in the past. So strictly speaking, you'd have to say, actually, I don't know if she's there right now because the light has taken, I don't know, a fraction of a nanosecond or something to get to me. Okay, but you could be super smart and say, after the light has arrived in my eyes, and I heard and said what she did, you can calculate back and say, by the time she said light or whatever, I was just scratching my head. So these 2 things happened at the same time. Then you could say, well, that defines a notion of simultaneity, which makes sense. Okay, so now most normal people would just find this a completely ridiculous question, but Einstein wasn't deterred by it, and we won't be deterred by it either. He came up with the following thought experiment to try and figure out what's with this notion of now. So we have one person who's watching a coach or whatever going by, and he has a friend who's on the thing that goes by. From left to right, this is what the arrow is supposed to say. And if this coach is directly centered in front of the guy who stands there, there are 2 triggers on each side at the same distance from the center. That'll trigger a light flash going off, like this. And the question is, do those light flashes happen simultaneously, or do they not? Well, you could say if this, for what this guy is concerned, forget about the train and the person on the train, it's much too complicated, just remove all that. You have those 2 light flashes, and you know that the speed of light is always the same. It doesn't depend on the observer. You know that both of those events are at the same distance. So both of those light signals arrive at him at the same time. And of course he'd say, well, yeah, sure, they're simultaneous. What else would they be, right? Okay, but how does it look like for the person on the train? Well, so the train or the coach or whatever travels to the right, and the trigger gets those two lights flashing. But now the train moves while the light travels. So the flash from the right, the light from the right, arrives at the person on the train first. So she'd say, well, actually, the one on the right happened first and the other one happened later. So now what? So we have two observers, they both come to different conclusions. Well, the conclusion is that this notion of simultaneity just isn't well defined in special relativity. It's not possible to come up with a notion of simultaneity that all observers will agree on. It depends on how they move relative to each other. The notion that we don't, the reason we don't notice this in everyday life is that if you don't travel very close to the speed of light, the difference is so tiny that you never notice the mismatch. But strictly speaking, it's there. So this is just one example of a very general behavior of special relativity. It's impossible to define any particular moment as now. Every observer has their own notion of now. Though strictly speaking, I should say that that's for what now elsewhere is concerned. So if you want to make a statement about what I'm doing while you're sitting there, that's the question, like what happens in this moment now over there. Now, the funny thing is that if you draw this insight to its logical conclusion, then it turns out that everyone's now could be somebody else's past or somebody else's future. And your past could be somebody else's present. So all those things become completely mixed up. In special relativity, it's just not possible to single out one particular moment as special. So if you want to assign any kind of reality to your present moment, the only thing you can do is that you have to assign the same type of reality to all possible moments in the entire universe. Strictly speaking, logically, there's another solution to this conundrum, which is to say that you can't say anything about what happens now elsewhere. You can only talk about what happens now for yourself. That's logically possible, but I'd say it's not the way that we, for our practical purposes, use the word now. We constantly speak about what happens now elsewhere. And Einstein's theory, the mathematics of Einstein's theory, just tells you can't do that. It's a meaningless concept. The conclusion of all of this is that you can't speak of a particular moment of the universe existing. You can only speak of the universe in its entire history existing. This is what it's become known as the block universe. In the block universe, there isn't just one moment which exists. It's the entire history of the universe that exists completely. The past, the present, and the future. And yes, we do perceive one moment as now, as a special moment, but all moments are special in this sense, which means they're not special because they're all the same. So there is a subtlety here, which I'll say a little bit more about in a few minutes, which is that this is for what pre-quantum mechanics is concerned. You have this strictly speaking deterministic theory of special relativity and later general relativity, in which you get this block universe in which all past, present, future exists in the same way. Quantum mechanics makes this a little bit more difficult because it tells you that actually the future isn't entirely determined. But for what the past is concerned, it's still correct. So the past exists in the same way as the present. So does the past still exist? Or we currently know, yes. What does it mean? Honestly, I have no idea. The way that I like to think about it is that we don't fully perceive the universe the way that it really is because we sit inside of it. whereas the mathematics describes the thing as a whole, and in some sense gives us this outside perspective that we can't really make compatible with our own perception. And this creates some kind of tension where other people think this just can't be true. But I have a lot of faith in mathematics, and I think it's actually correct. Okay, so then let's move on and say a little bit more about the quantum mechanics and stuff like that. Can information be destroyed? First of all, I want to say a little bit more about how the laws of nature work in physics. What we normally do in pretty much all theories that we use in physics is that we describe the initial state of the system at one particular time by collecting all the information that we can have about it. And then we have an equation that's called the evolution law, by which we can calculate what happens later. So we have this initial state, we apply this evolution law, we calculate what happens later, and this gives us a prediction. Now, the thing is that all those evolution laws, which we use in physics, are, as a matter of fact, time reversible. We can run them forwards and backwards. And indeed, it's what we do in cosmology. In cosmology, we often start with the present state of the universe, and then we calculate what has happened earlier, should have happened earlier, or might have happened earlier, which is how we arrive at this idea of the Big Bang. So we can use those equations forwards and backwards. Now, when I say that time reversible, that doesn't mean that time reversal invariant. It just means that we can use them forwards and backwards in time, but of course the future evolution can look very different from the past evolution. So what this means is that all this information in the states which describe the system is reconfigured by way of this evolution law, but it's never destroyed because you can use it forward and backwards. You can, at any time in the future, you can take your evolution law and calculate, in principle, not in practice, but in principle, you can calculate what happened earlier. And in principle, you could take the entire information about the universe at this present moment and calculate exactly what will happen in 100 billion years or something like that. All that's true for all fundamental laws we know, except the measurement in quantum mechanics and black hole evaporation. And so I want to say a little bit more about those. In quantum mechanics, we actually do have two different laws that describe what things do. So I know things sound a little bit vague. I warned you, it'll be a little bit vague in places. But basically, quantum mechanics should, in principle, describe everything. So whatever you want to describe, there's a wave function for it, how we do it in quantum mechanics, and then there's an evolution law for the wave function that tells you what the wave function does. But the weird thing about quantum mechanics is that the wave function doesn't actually tell you what you observe about the system. It just tells you the probability of what you observe about the system. So we have the wave function. From the wave function, we calculate the probabilities. Now, the issue is that once you have made an observation of, say, a particle of which you have a probability distribution, like you see here, 60% on the one side, 40% on the other side, you observe the particle on the right side, but then you know with 100% probability that it's on the right side. And this is the infamous collapse of the wave function, where you suddenly have to update what you know about the particle from this distribution to a certainty. So you start out with a lot of possibilities, and then suddenly you collapse them to this one actuality, you could call it. And the thing is now that this measurement update is an irreversible process. If you only know that you've measured the particle on the right side, you have no idea what the initial probability distribution was. Could have been this 60-40, could have been 90-10 or 10-90 or whatever. You really can't tell from making this measurement. So in this kind of process, you cannot deduce what the initial state was. And And yeah, wave functions, we normally use them for elementary particles like electrons and stuff like this. But this is just because we can't really observe quantum processes for larger things. It's not because we think they don't exist, it's just because they're hard to observe. In principle, the wave function should also describe the behavior of atoms and molecules and you and I and the entire universe. So this is a general thing. It gets a little bit more complicated if you talk about the entire universe, because then you have to ask who's doing the measurement. Okay, so that's not reversible. Measurements in quantum mechanics do destroy information, but the question is, do they actually describe what happens? And I would say we actually don't know, because what we do know is that this measurement process in quantum mechanics, the way that we currently describe it with this spontaneous collapse, is a huge problem. I think this is also what Einstein didn't like about quantum mechanics. I know people often say that Einstein was just wrong about quantum mechanics, but I think poor Einstein has been badly misunderstood. His issue was with the collapse of the wave function, because if it happens instantaneously, it's faster than the speed of light. Just mathematically, if you describe this collapse of the wave function, it happens in an instant everywhere. And of course, Einstein didn't like this, because he said, like, information shouldn't travel faster than the speed of light. So it turns out that if you look at what you can actually measure in quantum mechanics, this has no observable consequences. We can't actually observe the collapse of the wave function. We only observe the outcome of the measurement. So this is why it doesn't actually cause any mathematical problems, but it's still kind of, it doesn't really make sense, right? You think that the physics should obey the speed of light limit, because that works in cosmology and in everything else, except for the measurement process in quantum mechanics. That doesn't make any sense. And I'm totally with Einstein. I think there's something fishy about this measurement process, and it's probably just an approximation to what really happens. So there must be an underlying theory that explains what's really going on, which we haven't yet found. And I suspect that this underlying theory will actually be deterministic again, but this would be another topic entirely. And it's only my opinion, you know. I think a lot of physicists would actually disagree with that. Okay, so this is the measurement in quantum mechanics. The other example where a process might happen that is not time reversible is black holes. If something falls into a black hole, it might be gone forever. Now, at first sight, you might say, well, if something falls into a black hole, it's just hidden. Doesn't mean it gets destroyed. If I take something and I put it into a box and I close the box, that doesn't mean that it got destroyed, right? It just means I can't see it anymore. So what's the difference to a black hole? And indeed, this would have been a good answer before Stephen Hawking came and said, well, actually, there are quantum effects going on outside the black hole, and they lead to the evaporation of the black hole. It emits radiation. Actually, it emits all kinds of particles, but mostly it's photons and neutrinos. And in this radiation, there's no information except for information about the mass, charge, and angular momentum of the black hole. So very little information. Definitely not enough information to encode, say, everything that's written in a book. If you throw a book into a black hole. And that creates an irreversible process, because consider you have a black hole and you throw in different things with the same mass. Books, turkey, apples, whatever. You throw it in, it creates a bigger black hole. The black hole evaporates. And now all this radiation which comes out is this random Hawking radiation, which doesn't carry any information about what fell in. Eventually, the black hole is entirely gone, and the only thing that's left is this Hawking radiation. But it's always the same kind of random radiation, regardless of what you threw in. So you can't figure out what actually went into the black hole, and it's an irreversible process. And this leads to what's been called the black hole information loss paradox. I'm always a little bit unhappy with this name, but you know how it goes with nomenclature, it doesn't always make sense. The issue with calling it the black hole information loss paradox is that the first thing people ask is, what do you mean by information? And what's meant by information in this example is just all the information in the initial state. It gets lost. Some of it gets lost. And the issue is that in quantum mechanics, without the measurement, this shouldn't happen. Yet in black holes, it already happens without making a measurement. That's the issue. So those two things are just mathematically incompatible. So the odd thing that happened was that Stephen Hawking took gravity, Einstein's theory of general relativity, which is a non-quantum theory, combined it with quantum physics, calculated what happens around the black hole horizon, and arrived at a conclusion that's incompatible with the quantum theory that he started with. It's a very good example of a mathematical inconsistency, and this is why it's attracted so much attention. And physicists have tried since 50 years, or what was it, 72, I think. Yeah, it's more than 50 years now, tried to solve this problem. And they have found a lot of solutions, but none of them is really agreed on. I think most physicists believe that the black hole evaporation process is actually reversible. We just haven't figured out exactly why and what's going on. And I also share this opinion. It's probably a reversible process, but we would need to understand how the quantum properties of space and time themselves work to really figure out what's going on. So can information get destroyed? Well, that depends on what you believe happens in a measurement in quantum mechanics and in black hole evaporation. But if you'd ask me, I think the answer is no. This, by the way, so if you believe this answer, that it's no, is another way to see that the past still exists in some sense, because all this information about the past only gets reconfigured in other arrangements. It can't actually get destroyed because this time evolution is always reversible. Okay, then let's move on to the question, how did the universe begin? For this, we first have to talk about how modern cosmology works. It's based on Einstein's theory of general relativity. That's a complicated set of nonlinear differential equations. If you use them correctly and you put in all the stuff that we see in our universe, then you find that the universe expands. And we actually know this from observations. It's correct. The universe does expand. Actually, the expansion is getting slower, is getting faster. But this isn't so relevant at this point. The thing is that if it currently expands, then in the past, all the stuff in the universe must have been much more condensed. So it must have had a higher density, and specifically a higher energy density. And you can calculate the rate of expansion from all the stuff that's in it and from the equation of state of the stuff and so on. And it's a very powerful model, this modern cosmology that we can calculate from Einstein's theory. It has made a lot of predictions, for example, how structures form in the universe. The current idea is that in the early universe, we had some kind of hot plasma, which then started to collapse under the pull of its own gravity, and it started to clump, and then the first stars started to ignite, and they collected to form galaxies, and the galaxies merged and grew, and so on. And this is how the structures in our universe came about, eventually including planets with people crawling around on them like us. And it's made quite a few of rather specific predictions that turned out to be correct. So we do have a good model for how the universe evolved. But what happens with those equations, if we just trace them back in time, we run into a singularity at a finite time of about 13.8 billion years, 0.77 if you trust NASA. And this singularity is technically, so first of all, it's not in any one particular point, it's actually everywhere, so it's infinitely extended. A lot of people tend to think that the Big Bang happened in one particular place, but this isn't so. It's just an instant in time where the energy density was infinitely large, and also the curvature of space, they were both infinitely large. So that brings up the question of what the heck does this mean? Like that, the curvature of space-time was infinitely large. We've never seen anything being infinitely large. A lot of physicists, and I would agree with that, think that if something becomes infinitely large in your mathematics, it means that the theory really breaks down. This isn't something that can actually happen in reality. And we have some good reasons to believe this, because we have singularities that appear in other theories. For example, when we describe fluids with a theory called hydrodynamics, we sometimes have singularities appearing in the description of, say, droplets, as a pinch of a water tap or something. It forms this droplet shape, which has a very sharp point on one end. And technically, this point is a singularity. It has an infinite curvature. But we know that if we were to zoom into this pinch-off point of the droplet, what we'd find is that the water really isn't a smooth fluid, but it's actually made of molecules, and the molecules are made of atoms, and the atoms are made of smaller constituent particles, and so on and so forth. And there isn't anything really infinite about it. So this singularity is an artifact in the mathematics that we're using. And if it shows up, it just means that, strictly speaking, we should be using a better theory. And this is how physicists think about the Big Bang singularity, that it's just an indication that there's something wrong with this theory. We shouldn't be using it that closely, that far back in time, that closely to these large energy densities. But it's a little bit more complicated than that. Because remember how natural laws work. If you have a final state, because in cosmology we're trying to work backwards to the Big Bang, and this evolution law, then there's always an initial state that will give you the final state. So basically what this means is that the evolution law plus the initial state can exist in arbitrary combinations. Just imagine you took a different evolution law and you evolved it back in time from the current state. Well, then you can calculate what the initial state would have had to be to give you the current state. So strictly speaking, you can't really figure out what the initial state was from your, if you don't already know what the evolution law is. So you have kind of a degeneracy between the evolution law and the initial state. So how do we know what happened in the early universe if we could take whatever evolution law and just calculate what happened back then? Well, the thing is that you want a theory that explains what you observe. And generally, this will not be the case. If you take an arbitrary evolution law and you take the current state and you calculate it backwards in time, yes, you will get an initial state because that's how the equations work. But generally, it'll be a very, very complicated state. And with that complicated initial state, you can't explain anything. It's more difficult than the thing that you're trying to explain. So the way that cosmology actually works is that you're trying to find a combination of an evolution law and an initial state that is simple and that explains what we observe. And the current cosmological model is really good at this. An example which is fairly easy to understand is that if you look at the cosmic microwave background, which is all around us, that's radiation which is left over from this hot plasma in the universe. It has a particular distribution of hotspots and colder spots that you've probably all seen, and of which I should have added an image but forgot. So this is one of the data that we have about what happened in the early universe. But the other thing that we can look at is the current distribution of galaxies in the universe. They're more clumpy in some places and less clumpy in others. And this also gives us a density distribution. And those two things in our current cosmological model, they fit together. We have one initial state that gives us the right prediction for both the cosmic microwave background and this distribution of galaxies. Now, if you took any other evolution, it wouldn't work out. You could make up some initial state because there always is one, but it wouldn't be a simple one. And so it wouldn't have such a high explanatory power. So this is generally, I think, how it works in science. We want an explanation that is simple, and we go with the simplest explanation because that's what we consider to be the best explanation. And this is how we get to the Big Bang, because this is the simplest explanation that we have. We just take the equation, it fits to our observation. We haven't found anything simpler than just rolling Einstein's equations back in time. But what's now happened in the foundations of physics is that physicists really don't like the singularity, and they don't just like saying, we just don't know. So they've made up all kinds of other stories about what could have happened instead of the Big Bang. For example, there could have been a big bounce. So there wasn't a singularity or anything like it, but there was an earlier phase of the universe that collapsed. It didn't form a singularity, just some very dense soup, and then it expanded again. This process could repeat in principle infinitely often, which gives you a cyclic universe. There could have been an infinite time before, I don't want to say before the Big Bang, that's bad. Instead of the Big Bang, there could have been an infinite time in which pretty much nothing happened. And then at some point, the universe started expanding. Like, this is one possibility, which just mathematically you can make it work. There's the idea that time started at a particular place, so to speak. And before that, there was only space. So the universe started as a four-dimensional space. And then at some place in that space, I have to say, one direction of space turned into time. This is called the no-boundary proposal from Hartle and Hawking. There could have been either space or time, some kind of network, whatever. Some people have talked about five-dimensional black holes, string gases, colliding membranes, whatever. So there are like hundreds of those ideas. And they're not wrong. They're not wrong, at least most of them are not wrong. And most of them are compatible with our observations. So how does this work? Well, it's because as you go back in time, you can modify the equations at a time so early that we just don't have any data to tell them apart. And then you can use whatever story you like to spin and you wrap it in mathematics, and then you can get it published in scientific journals. So I really think that those are modern creation tales. We can't really say that they're wrong, but they're not really scientific either, because they add all this unnecessary clutter to our theories. So a good scientific explanation must be simpler than the thing you're trying to explain, and it should be as simple as possible, but not any simpler, as Einstein said. So unnecessary assumptions are not allowed. And the basic reason for this is that if you were to allow unnecessary assumptions in your theories, you could take any theory, take the standard model of particle physics or what have you, and just add the assumption, and God made it. So then suddenly you've made God scientific. So this is the basic reason why we can't allow unnecessary assumptions in science, because then science just would stop working. And all those stories for the universe are unnecessarily complicated. Now, I want to stress that this really doesn't mean they're wrong. It just means we can't tell whether they're right or wrong. And my friend Tim Palmer coined the word ascientific for this kind of theory. And when he came up with this, I said, that's ingenious. I'm going to use it. Now everyone thinks it was my idea, but it wasn't. Yeah, so I kind of started using this word ascientific as opposed to unscientific. And unscientific theory is one that's just wrong or that conflicts with the scientific method. Like if you were to say, okay, dancing makes it rain or something like that, that's unscientific. An ascientific theory is, for example, that the universe actually cycles. It doesn't conflict with anything we know, but we also can't tell that it's correct. So how did the universe begin? We don't know, and I think we may never know, because the further back in time we look, the fewer data we have, and I think at some point we'll just have to say, well, that's it, that's the end of the story, we can't go any further. I think we can certainly go back further than we can right now, but I think there'll be a limit to that. Okay, now it gets more esoteric as we go, as you see. Do copies of us exist? So this is a topic like I get constantly asked about. It's about the multiverse. You've almost certainly heard about. People love talking about the multiverse. It comes up in a lot of science fiction, also fantasy books, in movies, and so on and so forth. And it's not all just fiction. There's actually an underlying scientific law where types of multiverses have come up in theories, so to speak. The probably best funded one, you could say, is eternal inflation. So in eternal inflation, so first of all, I should say that inflation is the idea that the early universe underwent a phase of very rapid exponential expansion. There isn't any particular reason why this should have been the case, but astrophysicists like this for complicated reasons. Now, the thing is that if you look at this mathematics of how the universe is created in this eternal inflation, it turns out that there isn't just one universe created, but there are actually infinitely many of them created, and they continue to be created over and over again. So you have infinitely many big bangs, so to speak, just as they don't have a singularity, where the universe starts in a really small bubble, which then undergoes this exponential expansion and ends up being as huge as our universe or larger. And those universes which are created in eternal inflation, they could come with variations of the constants of nature, like variations of the mass of the electron or the mass of the Higgs field or the strength of the gravitational constant, stuff like this. This is called a landscape of universes. And in some variations, you can also combine it with the many worlds interpretation, which I unfortunately have on a later slide. So it was not particularly well organized, but yeah. What's the issue with this idea? Well, the issue is that we cannot make any observations about those other universes. They're completely disconnected from us. There are no observations that can refute or confirm that these other universes exist. You don't even have to go so far and believe in eternal inflation to see that something weird is going on in our universe. In Einstein's theory of general relativity, like the standard cosmological model, which I was talking about, which leads to the Big Bang, space is actually infinitely large. We don't actually observe this infinitely large space, so you could see it kind of, superfluous. Why not make do with a finite one? But technically, mathematically, it's infinite. And now you can say, well, let's just take this seriously. What does it mean? But remember that according to this theory, everything you see around you right now, including you yourself, came out from some small fluctuations in this initial hot soup of plasma in the universe. Now, if you have an infinitely large space, then all of those fluctuations in their particular configurations will repeat somewhere. And then, indeed, they will repeat infinitely often in all possible configurations. So what this means is that this planet, our entire universe, the solar system, wasn't just created once, it was created infinitely often in all possible minor modifications, because infinity is really weird. And so if you take this infinite universe seriously, and you believe that those initial fluctuations that gave rise to planets and stuff were really random, then you have to buy into this. And this is all well and fine, but the problem is no observations can refute or confirm that these copies exist, because we can only observe a finite part of the universe. And all this other stuff, which is infinitely far out there, we can never make any contact with. And then there's the many worlds of quantum mechanics. We already talked about the measurement problem in quantum mechanics, where you have this collapse of the wave function. You have this initial wave function gives you a probability distribution, and suddenly you have to update it. So the idea of the many worlds interpretation is that you just don't make this update. Instead, what happens is that all possible outcomes of a measurement happen each in its own universe. So suppose you have a particle that goes through a beam splitter and it has a 50% probability of going through and a 50% probability of being reflected. Now, in standard quantum mechanics, you would describe this with a wave function, 50% probability, and then you update it to 100 if you measure it on the left side, something like this. In many words interpretation, you would say, well, actually, there are two universes, and in one universe, you observe the particle on the left side, in the other universe, you observed it on the right side. And this doesn't just happen for photons going through beam splitters. It happens every time a wave function collapses in the standard formalism. So there are lots of those universes, and they're getting more as we speak. I have a lot of problems with this idea, but I don't want to get into it because then I'd still be talking 3 hours. But yeah, it's a thing, and it's another example of a multiverse, and you saw it coming. The problem is that no observations can refute or confirm that these copies exist. It's all well and fine to say, well, if I observed the photon on the right side, and was another universe in which I observed it on the left side, but what does it mean if you can't observe it? Right. So it's an interesting question why a lot of physicists actually believe those things are real. And I think it's because they take their mathematics too seriously. They have some stuff in their mathematics, and they think just because it's there, it's actually a real thing. And yeah, you can assume that it's real, but that's an unnecessary hypothesis. It doesn't follow from your mathematics that it's real. And if you assume that it's real, that it's not a conclusion that you draw, so science can't tell you that these copies are real, but it also can't tell you that they're not real. So I think this is also an example of an ascientific idea. You can't believe that those other universes exist. There's nothing wrong with it because we can never test it. But there's also no reason why they should exist. Okay, and this brings me to the last example. Can particles think? I told you this would get really esoteric. This is actually a question that people frequently ask me, like, how do we know that particles can't think? It's become a little more popular in the past couple of years because there have been a few books written about it. It's known as panpsychism. It's the idea that everything is a little bit conscious, including carrots. It just so happens that some of us have a little bit more consciousness than vegetables. And the idea is that the reason this happens is that everything, including elementary particles, has a little bit of proto-consciousness. And if you make bigger things, you combine the consciousness. And at some point, you get real conscious beings like us. So basically, that's the idea. Now, the problem with this idea is that if the proto-consciousness isn't physically real, and this is kind of an escape route that a lot of panpsychists use if a physicist comes across their path. is they say, well, this proto-consciousness isn't a physical thing, you can't measure it, and so on. Then there's just the notion of dualism, where dualism is the idea that the mind is separate from the physical world. And that's all well and fine, but then it doesn't explain anything. Like, you can't use something that is not part of the physical world to describe something that definitely is part of the physical world, namely people walking around and definitely appearing to be conscious. So what the heck is this supposed to explain? Again, it's not that it's wrong, but it doesn't explain anything. Like, we want to explain our observations. Like, why are things with brains different to vegetables? Like, this is one of the questions you might want to answer with your theory of consciousness. And then there are the panpsychists who actually think that the consciousness stuff is physically real. And then I have to say, well, then it better agree with physics, in particular with the standard model of particle physics, which you say here, so that you don't have to count, it's 25 particles. That, for all we know, make up everything in the universe. I found this quite amazing. It's 25 particles, that's it. The building blocks of everything. Actually, most of them we don't even use. But yeah, so that's it. And they all have certain properties that we collect in what's called quantum numbers. So quantum numbers are things like the electric charge, you've probably heard of, spin, weird stuff like the weak hypercharge and things like this. So it's basically a bunch of numbers that uniquely identify what the particle is. So I can give you the series of numbers and you could say, well, that's a tau particle or whatever. And the thing is now that those numbers predict what you see in particle collision. So this is an example of the observation of a particle collision that happened at the Large Hadron Collider. In this case, you have two beams of protons meeting each other head on, and then a lot of new particles are created that spray out to the sides, and they have detectors, and they recalculate the tracks that the particles took. The thing is now that you can use the mathematics of the standard model to calculate how many of those particles should be produced, of which type, and so on and so forth. And the result depends on those quantum numbers. If you were to add any kind of property to the particle, those numbers would change. And this is how we know that the elementary particles in the standard model are actually featureless. They can't have any consciousness on proto-consciousness unless this proto-consciousness is completely featureless, in which case, again, it doesn't explain anything. Now, there are some ifs and buts that we could go through. For example, there are certain types of quantum numbers that you can hide at very high energies or weak interactions and stuff like that. And yeah, you can do this, but again, then this explains situations that don't occur for things that we know are conscious, like you and I. So, do particles think? No, they don't think. Yeah, and this brings me to my end. In my book, Existential Physics, I have a couple of more questions. I also have a few interviews with people who, now that I think about it, I think they're all in the UK, seem to be spending a lot of time here. And it did help, as you can see, because my new book did find a publisher in the UK. Thank you for your attention.
All right. Do we have any questions from the audience? I'm sorry with the demo.
Thank you very much. Really enjoyed that talk. And even gave us new technology, which will ask questions. So, first of all, I agree with 99% of what you said, and that's because you're focused scientific, actually. And then you can't really disagree with science. So, that's hard. reasonably relevant. But you gave us a terminology, ascientific, and you gave us two instances where ascientific science would grant those subjects as ascientific. We began in multiverse, and then you gave us one where science would say, no, it's not really ascientific, the consciousness of particles. I'm curious to know if you think that morality is ascientific. Because that really, I was expecting you to tell us existential physics. How to deliver with that?
Well, I'm afraid I have to ask the obvious question. It depends on what you mean by morality. So, well, I would say that morals, and I'm very much a physicist, you know, morals are some kind of emergent properties that humans evolve who live in big societies. They're basically rules of behavior that we derive from our interaction and psychology and sociology. So it's a really complicated thing. So morals are not really a theory in that sense. So you can't really ask, is it scientific or is it ascientific or unscientific or what is it? It's just a thing in human society.
And can you just throw the box to people?
Hi. Regarding information, so you mentioned that information can't be destroyed. My question is, can it be created? If it can be created, does it need to be stored? If it can be stored, could we need to infinite information and running out of space? If it can't be stored, is it a physical property?
Yeah, right. So as I said, when I was talking about the information loss paradox, this word information causes a lot of confusions because the way that it's actually used when we talk about the black hole information paradox is that it refers to the information that encodes the initial state. So typically this will be all the information you need to write down the wave function or stuff like this, or all the particles and all their quantum numbers and so on. And this kind of information can neither be destroyed nor created. Now, when you're asking about other types of information, I don't know. Depends on exactly what kind of information you're talking about. If you look at the literature, there are like 10 different definitions that people have come up with.
Thank you very much.
So if you go back to what you said at the start, and you were talking about kids in school learning physics at the beginning, and you know they find it maybe a bit boring talking about pendulums, stuff of that nature. We see a lot of like documentaries on the TV, popular shows talking about stuff that borders on philosophy, what you describe as existential physics, and there's a lot of A-science in these sorts of things that you describe as A-science, and a lot of these questions come up. And there's not a lot of maths and stuff like that. And there are some people out there, like as kids, who may see these shows and be like, oh, what's going on with social physics? And then they come to the, you know, they go to sixth form and they go to university potentially, and they see that there's a lot of maths in physics. It's a very slow process, very rigorous process. Do you worry that we're trying to wrap kids into physics without knowing what really they're studying, and they're expecting something very qualitative and philosophical, and they're expecting something very qualitative and philosophical, but really they're getting something completely different, and that's not really positively impacting the field of physics?
Well, so honestly, I don't so much worry about the kids. I think the kids, I think the kids will be fine. You know, I think young people, you know, they just figure things out. You know, they start studying one thing or the other, and if they notice it's not the right thing, they go on to study something else. Like, I mean, I started studying mathematics, and then I ended up in physics, and I've had friends who studied law, and then they ended up in informatics, and you know, so I think that's a normal progression of life, that you try things out and then you readjust. What I'm a little bit more worried about is the people who don't go to study physics, who never find out, because they go away with this impression that physics is all vague, blah, blah, and you can just make up your stuff. And a lot of those people end up cooking up their own theories of everything, and most of them end up in my inbox sooner or later. And it's not just the problem, it's not just my inbox. I think that people don't fully understand just how rigorous physics is. And it's not just physics, you know, you could say, well, who cares if they don't really with climate physics. I think they don't really understand just how rigorous those analyses and the models are and so on. They think it's all just words, more or less, and then they sprinkle some data over it. And you know, where this issue comes from is that science communicators try to make things simpler. And I totally understand that, because you want to reach a lot of people. But the problem with this is that a lot of people get away thinking it's simple. So I think every once in a while, we just need to remind people that there's more to it than what we just told you. Right? There's actually stacks of textbooks or whatever that you have to make your way through to really understand it.
Hi there. I have a question which I hope fits into the category of existential physics. What is a measurement in the context of quantum mechanics?
Yeah, that's a most excellent question on which I have another talk if you want to stay another 90 minutes. So we don't know, to make a long story short. So the way that we treat a measurement in quantum mechanics at the moment is that a measurement, we know it when we see it. You know, a detector is the thing that makes a measurement, and a measurement is the thing that the detector does. And so far, this has worked just fine, because normally there isn't much ambiguity of what we mean by making a measurement. You know, the experimentalist just knows. But now what's been going on the technological side, which I find very interesting, is that measurement devices are getting smaller and smaller and smaller, whereas the things that they're trying to measure, putting them into quantum states, are getting larger and larger and larger. So you get into this crossover where it's actually no longer clear, like, what's the thing that you're trying to measure and what's the measurement device? And so I think that sooner or later, physicists will have to find an answer to that question.
So throughout the history of physics, we've always used these mathematical, essentially differential equations to describe the evolution as we describe. And we keep on essentially making these differential equations more complicated and complicated to apply to more situations. But do you think it's kind of naive in a sense to assume that at some point we'll be able to describe everything with a mathematical equation? Aren't we, in a sense, kind of like you're adding operands at Taylor extension, trying to get closer and closer and closer, but are we sure that the final thing is something we can formulate in a mathematical way?
So I think that there are two questions in your one question. One is, can we do it with differential equations? And then can we do it with mathematics at all? So when it comes to the differential equations, I think physicists have gotten a little stuck on that. And I'd actually be happy if there were more physicists trying to figure out if we can do it with different mathematics, you know, something that doesn't need an initial condition. And there are some approaches in that direction where you have a more holistic picture of the universe with some kind of consistency condition, basically, that gives you a time evolution, but not by a differential equation. And I think this is one of the possibilities where I could actually see that we might be able to figure out how the universe began. Because in that case, we don't need the initial state. Now, do we maybe rely too much on mathematics? I think most physicists would say it's got to be mathematics. Mathematics is the language of nature and so on. But personally, I'm not all that sure, just because mathematics is a fairly recent discovery, so to speak, if you look at the history of mankind. And who knows what we'll come up with in a million years if we survive that long. So maybe there's something better than mathematics that no one has ever thought of. How am I to exclude this possibility?
When writing this book, did you find any textbooks that were like really helpful? Okay, so.
Textbooks. Well, there are a lot of different topics, right? So anything in particular? Yeah, what's his name? Sorry, there's a quantum information guy in Cambridge, the other Cambridge in the United States. What's his name?
Isaac.
No, sorry, I'm terrible with names. I'm sure it'll come back to me when I don't need it. Give me 1 or 2 minutes, and maybe I'll know later.
We'll take one last question. You want to ask also?
Sorry, when you're talking about all your ascientific theories, there's lots of parallels to religion. What do you think your philosophy on this? What do you think the implications are on theology?
Well, that's an interesting question. So, you know, I don't know a terrible lot about theology, but basically I'd say it means that theologists are safe from physicists because, you know, there are certain ascientific questions that I think neither physics nor any other area of science can ever say anything about.
Yeah.
Hi. For like many of the ideas you mentioned in the talk, for example, like the notion of now and the consciousness of the proto consciousness of everything, and like the measurements or observations in quantum mechanics. Do you think like the kind of physiological paradox thing, the philosophical contrast they made is somewhat related to like our own viewpoint, like only from our own perspective, but while the physics laws they seem to be wanting to apply to what we regard as like every point in space time.
Well, so I'm not entirely sure I fully understand the question, but let me just generally address the point. I think it's certainly true that our own perception and our psychological preconditions, so to speak, influences the types of laws of nature that we come up with to begin with. For example, since somebody else just asked about differential equations, I think the reason that we use differential equations is because it agrees very well with our own perception of how things happen. You know, something has an initial state, then we observe what happens afterwards. This is the way that we perceive reality. And that might not be the best mathematics to use. So and this is certainly something to keep in mind whenever we develop new mathematics, that we might be biased by the way that we experience nature. Now, is this an issue that we can ever overcome? I doubt it. You know, we might be able to extend our minds in all kinds of ways. I don't know, by implanting chips or what have you. But in the end, I think there'll always remain a bias so long as we are separate from the entire universe.
Okay, thank you.